Okay, so this talk has a couple of false starts, and this is the first one. This is a Stack Overflow post that I wrote 6 years ago, wondering about what my code was. It's not so important, but the thing is that it sort of sets the background a little bit for this talk. And to disturb you all, anyone else than me have seen this and that, and been disturbed about it?
We are now.
We are now, thank you. Okay, so I'll start off with a little bit of propaganda. One of the nice things of working with Clojure is that you get to work with a lot of open source libraries. So I would really like to encourage you to be nice to your open source maintainers. A lot of them do their work on the libraries in their spare time and for free, and we should all be very grateful for the time that they put into that. If stuff is not as you'd expect them to be, or if you find faults, do create issues, don't just go silent. And also, if you're capable of fixing it, please do submit PRs. And be polite. That makes it much easier for you to be heard, and it's much nicer for all of us if we all behave. Also, support your favorite open source projects. There's this organization called Clojure Together. Who's a member here? Who's a developer member? Shame on you, the rest of you. Who's working for a company that supports Clojure Together? Good, thank you. And if you're not a member, please do become a member. And if your company's not a member, make sure that your boss pays for that. I want to give a special shout out to a tool that I use every day at work. I use it every day since I started using Clojure. It's Cider, and I think Bozidar is sitting there taking a photo of this slide right now. Should we give him a big hand of applause? And we all know why we use it. It's because it rocks, right? Okay, so I'm Erik. I work as a tech lead. I work as a tech lead at a company in Oslo called OurDoc. I'm a grumpy old programmer enjoying Clojure. And I enjoy more working in legacy code than what I do working in Greenfield. And as such, I'm much better at rewriting old code than hammering out new stuff. Most of the stuff I do is CRUD applications. According to Chaz Emmerich, that's basically what we all do. And that means that the problems that I encounter is code that's different from the code that you would write if you're writing libraries and such. And the main difference is that my programs tend to have state, and another is that they're often called by frameworks. And the programs that I write, they tend to produce side effects, and they tend to be written in a haste, and oftentimes with unclear or not well understood requirements, if the requirements are there at all. And that gives me a workday of legacy code. It's convoluted. It's been written by many people over long periods of time, and you sometimes wonder if the solution that you're looking at, if it's the first solution that ever came to mind, or if it's actually the last one. I have some code in our recent project where one of the anonymous functions is called foo. So you're looking through this bit of complex code and you see the thing that really does the meat. That's called foo because the author couldn't be asked to name it properly. This code is also very often very hard to test because it's very tied to its environment. So to be able to test stuff, you have to mock out either the database or the HTTP stuff or wherever we have our state. And everything is intertwined, and state is generally handled all over the place. And as I mentioned, I work at a company called OurDoc, and we're in the enterprise architecture space. That's not so interesting here. The interesting bit is that it was founded 5 years ago on a bet on Clojure. The Clojure backend was written initially by one person. They got 2, and now we're 5 people working on that backend. And the reasons Clojure was chosen, at least the 2 official ones, was that it would give us a competitive advantage in terms of delivering features. It would be easier to write code faster, get stuff out in production faster. And the other thing was that it would be easier to hire better developers. And I might be a proof, sort of the exception that proves that rule. But what I've seen from hiring at OurDoc is that we've had much better applicants than what I've seen in previous jobs. And we actually get people to apply to our jobs. That hasn't happened before. And I also joined OurDoc simply because they chose Clojure. And if some of you have seen the videos from the conch, a guy named Oliver Idle was talking about this in his talk on developing a medical image viewer for ClojureScript, where he said that Python developers joining their shop, they wanted to not do back-end work. They wanted to go into machine learning, but Clojure programmers, they were happy as long as they got to program in Clojure, and that's basically me. One of my questions that I like to ask, and I'm wondering about, is does Clojure really scale? I mean, it works really nicely when I'm working on my personal pet projects and everything is 5 lines advents of code, a threading macro. But how does this scale to an application that lives for years with different developers joining in and moving on over a long period of time? And I think that the code base that we have now, which is about 27,000 lines of Clojure, and which is supported by some 14,000 lines of tests, proves that it's actually working. But we'll get onto that. But after having worked at OurDoc for a while, my CTO, he asked me, so what do you think about our code base? And I told him that it was whispering something to me, but it was kind of hard to figure out exactly what it was saying. Because this is not the Clojure code that we write. This is your start of, when you first start Clojure, this might be where you're starting at. But we normally write it like this, right? The problem was code like this. And why this code is bad, or in my opinion is bad, I'll come back to that a little bit later. So, the agenda. We'll start by a problem statement, then I'll look at some code layout, and then I'll talk a little bit about composability. And this quote I just had to have in here because I like it. So that's why we need a problem statement. So I want to talk about your typical Java web app backend thing. And the problem with our code is that it looks very much like that. And even though I stopped coding Java sometime sort of in 2014, this is what it looked like when I was coding Java. You have a REST API which talks to the business logic, which talks to the persistence. This is your run-of-the-mill 3-tiered architecture from EJB or something. And your code tends to look like this. You have a controller that calls down to the service, and the service calls down to the repository, and then it goes back up again. And this kind of looks okay, but it isn't exactly functional programming, I think. So what is functional programming? It's hard for me to stand here in front of you and sort of define functional programming, but I would like to give an idea of the important parts that I think are important of functional programming, and how to transform your not-so-functional code into something more functional and bring some terminology and resources forward that I've found that can help you identify this. So many of us, when we start out with functional programming, we sprinkle some map filters and reduce over the code base, and we're halfway done. But that is just a little piece of what is functional programming. I think if you've been programming in Java 8, you might have started to use optionals. And at the beginning, what you do is you look at an optional and you see, oh, I don't have to test for null anymore. But you're basically still doing the same kind of code. Whereas after a while, you see that instead of testing for it, you can map over the optional, and your code suddenly starts to not concern itself with the absence of things. So you can write whole bunches of code which just assumes that stuff is there. And you can put the check for the absence of stuff out at the edges of your application. And that is how you start to leverage these tools. And we have to talk about code layout, because that's sort of where this ends up in a way. And I think the man that tweeted this tweet might be in the audience. And I think what he was thinking about here was in SICP, there's this notion of stratified design or stratified architecture, where you basically build your application from small building blocks, and the small building blocks, they turn into bigger ones, and you don't go too far down from a top level down to the level below. Erik has a great podcast on this recently. But most Java programmers have misunderstood this thing with stratified design, and they're doing this, right? The three-tiered architecture. And one of the reasons I like Clojure is that you can write a lot more concise code than what you do when you write Java. And there is a reason why that is important, because code size tends to dictate how you organize your code. And there's this thing called the Norris number, which basically says that the amount of code that a new beginner can hold in his head without that being a total mess is around 1,500 lines. And there's a guy who's called Lawrence Kesselhout, who's written a blog post that expands on this. And he says that when your code is under 2,000 lines, you can write any tangled garbage and rely on your memory to save you. Basically, what this says is that if your application in Clojure or Java is less than 2,000 lines, you can have it all in one namespace. Wouldn't necessarily recommend that, but you can do that. And then he says, thoughtful class and package decomposition will let you scale to up to 20,000 lines. And how do we do that in Java? Because if you open up a normal Java application, what you'll see at the top level is a bunch of controllers. You see some services and some repositories. And the reason why we do that is that it's totally generic. And it being totally generic, it's easy for tools like Maven to make the directory structures for this. There's also this thing that you know that any Java application that's going to be worth its while is going to have somewhere between 10 and 100,000 lines of code in it. So you know that you're going to have to structure your app in this way anyway. But the problem with this is that your business logic becomes scattered around in all these layers, and it's not very easy to sort of grasp what is the business logic. And of course, the other thing is that just like a bland mission statement, apps consisting of controllers, services, and repositories doesn't help you to reason about your application. So when you write code in more expressive languages like Clojure, you tend to end up with an order of magnitude less code. Put it another way, maybe your 20,000 lines of poorly written Java could be written in 2Ks of beautiful Clojure. And what does that mean for your layout? It means that you can have it in one file or two. So let's jump on to composability. And it's my claim that when we write code, we don't often think in terms of composability. That is how the different pieces of our code is ultimately going to be put together. But in order to talk about how our pieces of code can be composed, we need to look at how we can decompose them. The front-end bit of our application is written in Java, and I like to compare that to a prime number. simply because a prime number can be factored into 1 and itself. So it's basically decomposable. Non-decomposable. And I want to go through a couple of ideas. And the first one is described in a talk by a guy named Gary Bernhardt. You might know of him. This talk is called Boundaries. And what he explores there is this notion of a imperative shell and a functional core, which means that you have a wrapper around your application where you take care of all the goo that is figuring out how to connect to different stuff. And then in the functional core, that is where your business logic resides. James Shore, a JavaScript guy, has a great blog post in Testing Without Mocks, where he describes what he calls an A-frame architecture. So this is yet another picture of your normal Java 3-tiered thing. But what he suggests is that you do it like this, so that your infrastructure and your logic is not allowed to talk to each other. They have to do that through the controllers. And what you get then is something what she calls a logic sandwich, where the data is read from the infrastructure layer and then processed by the logic layer and then written back into the infrastructure layer. And the beauty of this is that then each layer can be tested independently. But the metaphor I want to explore the deepest is and show examples of is from the book Elements of Clojure. Who's got this book? Good. Who would buy this book if it was in print? I would. Can we ask Zach to do that? Because I really want one of those copies. And I think he just wrote the final edition of it this last week. And if you haven't read it, haven't bought it, please go do that. And this book, he writes, tries to put words to what most experienced programmers already know. And that's somewhat the feeling that I have when I'm standing here talking to you about these things. But in the fourth and final chapter of this book, he discusses composition, where he introduces this notion of a process. And he says that a process, as defined here, is the smallest unit of standalone computation. So a process, you might think of that as a program, although a program might also contain several processes. And we have these three basic phases of it. So you have the pull phase, where data is pulled in from the environment. This is reading a file, receiving data on a socket, or getting some input from a user terminal. Then you have the transform phase, which is invoked by the pull phase, and this phase will have all its data handed to it, and will only transform the data and return it to the next phase, preferably with a description of the effects we want to have performed on the environment. And then finally, we have the push phase, which is responsible for pushing the transformed data out to the environment again. So if we look at this, it's quite easy to see how this relates to Clojure, right? Because it's basically just threading. So I want to explore this a little bit in some code. And let's first have a look at finding anagrams in a list of words that is stored on a disk. This is one way of figuring out which words are anagrams of each other. I'm not going to do that, but the thing here is that R and ear are anagrams, and dogs and gods are also anagrams. And our task here is to write on each line from that list of words, the words that are anagrams of each other. This is how you might want to do it in Clojure. Luckily, Cider has this thing which is fully thread expression, and that gives you this, which is much more readable. So we start by reading the file, and we split it into text files, or split it into lines, so it gives us a list of words, which we then group by the frequencies of the characters of those words, and group by here, A group by returns a map where the keys and the groups, keys are the groups and the vals are the values in that group, and we take those values. And then we remove the ones that contains less than 2 words. And we start assembling our output by joining the anagrams with space. We add a new line for each string of anagrams, and then finally print them, right? So I tend to use stuff like this in job interviews. And if our candidate gets to this, the first thing I ask them is, so how do you want to test this? Or can you write a test for this? And they go, sure. And then they see that this is a side-effecting function, right? There's no output of this thing. It prints to the console. So what we do here is that we're pulling from the environment, and then we're doing the transformation, and then we're again pushing out to our environment again. So if you write it like this instead, you have the business logic, which is green here, and it's very easily testable. And it's also decoupled from its environment, and it can be used in a host of different other settings, not just reading from a file and printing to console. And then you could, of course, make 2 other functions, and you're good to go. So I want to spend the last of this talk showing you some examples from our code base. My boss is not too happy about this because he wrote most of it. But we had this, this bit of code here. And the offending thing is this call to friend current authentication. Because what it does is that it pulls data from the environment. This is global state in the middle of a very nice little piece of business logic. So if you instead just pass that in as a parameter, you would have code that is super testable, and you can move it between front end and back end, and you can use it with any other authentication library that you would want. I think we might want to change out friend. And of course, you could test it, as I said, without resorting to mock objects. And then we have this other function here, or this set of functions. And you see that with metadata is passed a document from another face, but deep into created by details, we are pulling data from the environment again in the function get user by ID. So again, we pull it out, and we refactor out the function that is pure and nice to work with. Now, one could argue that with metadata could have been passed the creator and the updater also, but it isn't done because reasons. So the last example I want to show you is one that really looks a lot like Java code in Clojure. And I called it from Java to process, or extract method considered harmful. And before we start, I like to explain a little metaphor that I have and that I like, or it might not even be a metaphor, but I like to write code with wide call stacks, if that makes sense, instead of code with deep call stacks, right? Wide call stacks are normally what when I do threading, that's basically what I think about. I think a wide call stack, whereas when you're calling functions at the end, you get a deep one. So let's have a look at this one. Even though this is written in Clojure, it's basically Java. And the red code here shows how you were pushing data onto the environment via HTTP. And let's just have a look at this one thing here. We can easily do extract method on this thing. That's what you do in Java. And what you'd end up with is something like this, where you've avoided some duplication, and you also got more consistent error messages, but the logic of your application is as coupled to its environment as it previously were. So let's not do that. Let's rather introduce this green function here, org with plan, which transforms the data and then creates some new data which describes the effect that we want to have on our environment. And now suddenly it's testable. And there's also nothing that ties this bit of business logic to our method of choice for affecting our environment. So does this all matter? I don't think what I've shown is anything new. It's been described. And it might just seem like I'm moving code around for the fun of doing that. But it's actually at the core of what I consider to be functional programming, namely dividing your code into side-effecting functions and pure functions. And that helps you by decomposing the code in such a way, you remove cognitive overhead. There's less moving parts inside the functions, which can fail in ways we don't want to think about. Testing becomes easier because the need to create mocks and stubs and observe how these are called disappears. It also makes our integration tests simpler since they can focus only on the happy paths, whereas the unit tests can handle all the complicated business logic. This means less complex tests that actually runs a lot quicker. Also, our business logic becomes less tightly coupled with our environment. Now we're free to change to a real database. I didn't mention that we use MongoDB, and I will take no questions on why we chose that. Or even we could move our code from the client to the server or vice versa if that's ever needed. So in closing, map, filter, and reduce are necessary, but not sufficient. Code organization is important. And do split between pure and non-pure functions. And the reason I try to write as simple code as possible is that I cannot understand complex code. And for me, the question that I posed when I started at OurDoc and I'm still pondering on, does dynamic typing scale in an organization and in a big code base? It seems to do. But we are supported by an extensive test suite that was written by a coworker. And after I joined, I think that the coverage percentage dropped, which is not something I'm very proud of. We use a linter. We use Eastwood. It catches a lot of bugs for us. And we have 3 versions of different libraries for handling schemas. We have CLJ schema, we have schema, and we have spec in place. And that also helps us a lot. And when you choose to use a MongoDB, make sure that you have a schema somewhere, because it's really scary to have an HTTP or have an API where you receive a JSON blob and you just stick it in a database, and nobody knows whatever got in there. Thank you.
Thank you very much. That was another excellent talk there. Is there any quick questions we've got for Erik? Oh, yes, there we go.
Thank you, Erik. What slide software are you using? What presentation software are you using?
That's Keynote.
Fuck. It doesn't work on Linux.
It looks nicer. Any other questions? No, no, no. Yes, going 1, 2, 3. Let's go. Let's have a break. Thank you very much, Erik. Thanks again.